All right, let's talk about the engines that power pretty much our entire digital world. Servers. Today, we're going to trace their evolution from the most basic, simple designs all the way to the supercharged systems we rely on every single day. Let's dive right in.
Ever stop and think about that? How does one website, one service, feel instantaneous for you and millions of other people at the exact same time? I mean, it feels like magic, right? Well, it's not. It's actually this incredible story of smart design, of evolution, and that's what we're going to unpack today.
You know, at its core, every single server on the planet is trying to solve the same problem. It has to deal with this constant storm of requests coming in from everywhere. And its job is to juggle all of them as fast and as efficiently as humanly, or well, technically, possible.
Okay, so this right here, this is basically the map for our whole journey. You've got the clients, that's us, on our phones and laptops, connecting over the internet. But before our requests hit the servers that actually do the work, they go through this really critical piece called a load manager. Just think of it as the ultimate traffic cop for the internet, making sure every request gets where it needs to go.
So how does this traffic cop actually decide where to send everybody? Well, it's got a whole playbook of smart strategies. It could just go in a circle, that's called round robin. Or maybe it sends you to the server that's the least busy at that exact moment. There are all these different techniques, and they all have one goal: to spread the work out so no single server gets overwhelmed.
Now, if we're going to talk about which server designs are better, we need a way to keep score. Our first metric is throughput. It's pretty simple. How many requests can a server chew through every single second? This is our measurement of pure, raw power. And with throughput, bigger is always better.
And on the other side of the coin, we have latency. This is how long it takes to handle just one request, from start to finish. This is the one we feel. Is the app snappy? Is the website fast? That's all about latency. And for this one, you guessed it, lower is always, always better.
But here's the thing. A good average speed isn't the whole story. What about the unluckiest users? The slowest 1%? That's what we call tail latency. A system can be super fast on average, but if a few people are having a terrible laggy experience, then it's not a predictable system. And taming that tail latency, that's one of the biggest headaches in modern server design.
All right, so we've got our goals. We want high throughput, and we want low, predictable latency. Let's wind the clock back and look at the first stabs of building a server. These are the simple, one-at-a-time designs, and they're the real starting point of our story.
The most basic design you can imagine is the single-process server. Think of a kitchen with just one chef. He takes an order, he cooks the whole thing, serves it, and only then does he even look at the next person in line. Super easy to set up, right? But the second that chef gets a slow order, maybe something takes a long time to bake, everybody else is just stuck waiting. The result is just awful throughput and latency that's through the roof.
So the obvious fix seems to be, hey, if one chef is a bottleneck, let's just hire more chefs. This brings us to the multi-threaded or multi-process model. Here, a dispatcher gets a request, and poof, it instantly creates a brand new worker, a new thread, just to handle that one single request. And this sounds perfect, doesn't it? If one request gets stuck waiting for something, it doesn't block anyone else because they all have their own personal worker. So it just makes sense. The more threads we add, the faster the server gets, right?
Wrong. And this is where the story gets really, really interesting. Take a look at this graph. The red line is our throughput. As we add more workers, it goes up and up, looking good, and then boom, it completely falls off a cliff. At the exact same time, the blue line, our latency, which was behaving nicely, suddenly shoots to the moon. Adding more workers didn't just stop helping. It made everything catastrophically worse.
So what on earth happened? The bad guy here is something called overhead. The computer's processor has to jump between all these different threads. It's called context switching. And when you have thousands of them, the system ends up spending all its time just trying to manage the workers instead of letting them do any actual work. It's a fatal flaw, and it hits both multi-threaded and multi-process designs hard.
This total performance collapse, it forced everyone to rethink the entire strategy. Instead of just brute force, throwing more bodies at the problem, designers realized they had to start working smarter, not just harder. It was all about efficiency.
And that brings us to the thread pool. This is a much smarter idea. Instead of making a new worker every single time, you create a fixed number of them right at the start, maybe 16, right in that performance sweet spot we saw in the graph. Then, new requests just line up in a queue. Whenever a worker finishes a job, it just goes to the queue, grabs the next one, and gets back to work. It's brilliant because it gets rid of all that crazy overhead and stops that performance disaster from ever happening. But of course, the evolution didn't end there. The next big breakthrough was a total paradigm shift. It's a whole new way of thinking called the event-driven model, and its motto is basically, stop waiting around and start juggling.
So to get this, you have to understand the difference between blocking and non-blocking I/O. And all the old models, when a worker needed a file, it would just stop. It would block, sitting there, twiddling its thumbs, doing absolutely nothing until that file arrived. Non-blocking I/O completely flips that on its head. The worker says, hey, operating system, go get that for me, and just give me a shout when it's ready. I've got other stuff to do. This lets one single thread manage a ton of tasks at once.
And this is what it looks like in practice. At the heart of it all is this thing called a selector. It's juggling all the different connections, but instead of checking on them one by one, it just asks the operating system, hey, out of all these connections, does anyone have something for me to do right now? It gets a notification, an event, it handles it, and immediately goes back to asking. It never, ever waits. And that's how a single process can handle thousands of connections with incredible efficiency.
So now we're at the cutting edge. The most powerful modern servers today don't just pick one model. They're hybrids. They take the best ideas from everything we've talked about and combine them into something way more powerful and resilient. This design, called SEDA, is a perfect example. The best way to think about it is like a high-tech assembly line for data. A request comes in at one end, and it moves through these specialized stages. One stage parses it, the next checks a cache, the one after that might talk to a database, and so on, all the way down the line until a response is sent back out. Each stage is an expert at doing just one thing.
And here's the truly brilliant part. Each one of those stages on the assembly line is its own little intelligent system. It's got the event queue from the event-driven model, and it's got a thread pool from our Work Smarter model. It can even adjust how many workers it has on the fly depending on how busy it is. This makes the whole system super robust and stops bottlenecks before they can even start.
Wow. So we've come a long way, right? From that one lonely chef trying to do everything to this fully automated robotic factory. What this whole journey really shows us is that server design is always about making smart trade-offs.
And this table just lays it all out perfectly. Look, those early designs, super easy to program, but their performance under pressure is, well, bad. The thread pool model got us that high throughput we wanted. The event-driven model got us great throughput and good latency, but man, it is a nightmare to program with. And then you have SEDA, which kind of gives you the best of both worlds. Amazing performance, but it's much easier to work with because of that clean assembly line design.
So the biggest takeaway here is that there's really no single best server design. It doesn't exist. There's only the right design for the job you're trying to do. It's this constant balancing act between raw speed, predictability, and just how complex you're willing to make your life. So the real question, the one I'll leave you with, is this. If you were building the next big thing, what trade-offs would you make?